This lesson has been developed in the framework of SCILED project.
Module 1, Footwear Performance and Comfort. Unit 5, Testing Standards and Equipment for Evaluating Comfort and Performance.
Lecture 5.2. Testing Standards and Equipment for Evaluating Comfort Aspects. This lesson is structured as follows: thermal comfort and breathability, thermal insulation, softness and lightness, biomechanical comfort. Thermal comfort of footwear and breathability. Thermal comfort. The thermal comfort is a complex topic because involves the combination of several factors, including the materials used for footwear and their properties such as water vapor permeability and water absorption and desorption capacity, and thermal insulation. For example, thermal insulating materials will minimize the heat loss from the inside to the outside of the shoe, and breathable materials will promote the elimination of sweat to outside of the shoe. The footwear models and constructions. For example, a shoe that promotes a higher or lower thermal insulation and a higher or lower breathability will influence the temperature and wet sensation of the feet. Ventilation is another relevant issue when considering thermal comfort. Good ventilation inside the shoe helps to eliminate the humidity. The environmental conditions. For example, a shoe for winter or summer, or a shoe for Nordic or Mediterranean countries, or a shoe to be used by a farmer have different requirements and needs in terms of materials and constructions. The characteristics of subjects and physical activity. The heat and sweat release vary from subject to subject, it being necessary to eliminate heat or moisture to keep thermal comfort properties. Therefore, for the development of footwear models it is necessary to consider all these aspects and test the materials and footwear for final validation. Regarding materials, it is important to evaluate the water vapor permeability and absorption, water absorption and desorption, and thermal conductivity.
Water vapor permeability and water vapor absorption. The standards ISO 20344-6.6 and ISO 17699 describe methods to evaluate the water vapor permeability of lining and upper materials. Water vapor permeability is defined as the amount of water vapor a material will transmit through its structure expressed as mass of water transmitted per area of material per hour. In this method, the test piece is fixed over the opening of a jar, which contains a quantity of solid desiccant. This unit is placed in a strong current of air in a conditioned atmosphere. Then, the air inside the container is constantly agitated by the desiccant, which is kept in movement by the rotation of the jar. The jar is weighed in order to determine the mass of the moisture that has passed through the test piece and has been absorbed by the desiccant. Water vapor absorption is the amount of vapor a material will absorb in a specified time expressed as mass of water per area of material. The same standards describe the test method to determine the water vapor absorption. In this method, an impermeable material and the test piece are clamped over the opening of a metal container, which holds 50 milliliters of water, for the duration of the test. Water absorption of the test piece is determined by its difference in mass before and after the test.
The above values are the recommended values of water vapor permeability and water vapor absorption of lining and upper materials for occupational and casual footwear. The specifications can be found in the standards N 20345, N ISO 20346 and N ISO 20347 in the case of safety, protective and occupational footwear. The technical reports ISO TR 20879 and ISO TR 20882 describe the specifications of upper and lining material used in school, casual, cold weather, men and women's town, fashion and children footwear. For more information, please consult these standards and technical specifications. For example, upper materials for casual shoes should have a value of water vapor permeability equal or greater than 0.8 mg per squared centimeter per hour. If the value of water vapor permeability is less than 2.0 mg per squared centimeter per hour, then water vapor absorption should be equal or greater than 8.0 mg per squared centimeter. In the case of occupational footwear, the upper should have a water vapor permeability higher than 0.8 mg per squared centimeter per hour and a water vapor coefficient greater than 15 mg per squared centimeter. The coefficient value is obtained from the water vapor permeability and water vapor absorption. The lining materials have more exigent recommended values, for example, they should be more breathable than upper materials. During the design conception and footwear production, it is necessary to consider the breathability of materials by itself and together in the type of bonding to prevent the glue from compromise the breathability of materials.
Water absorption and desorption. The water absorption is the gain in mass per unit area of the test piece due to water absorption during one or more specified periods of time, and the water desorption is a percentage loss in mass of the test piece, expressed in terms of mass and water absorbed. The standard ISO 22649 describes two types of methods to evaluate the water absorption and desorption of insoles and insocks. Method A determines the water absorption and desorption in static conditions, and Method B determines the water absorption and desorption in dynamic conditions. The equipment presented in the Figure 4 is used in Method B. As an example, this table presents the recommended values of water absorption and desorption for insocks for occupational footwear and insocks for casual footwear. The specifications can be found in the standards N 20345, and ISO 20346 and ISO 20347 in the case of safety, protective and occupational footwear. The technical report ISO/TR 20882 describes the specifications of insocks used in school, casual, cold weather, men and women's town, fashion and children footwear. For more information, please consult these standards and technical specifications. The recommended values for water vapor permeability are as follows. For occupational footwear, the absorption shall be greater or equal to 70 mg per squared centimeter and the desorption shall be greater or equal to 80%. For casual footwear, the absorption shall be greater or equal to 70 mg per squared centimeter and the desorption shall be greater or equal to 60%.
New methods have been developed to measure the temperature and relative humidity inside the shoes, using sensors. Tests are usually performed by a selected panel of subjects in a treadmill, at constant velocity, in room-controlled conditions. Face type of tests can also be done in real conditions by measuring the temperature and relative humidity during one or several days. The graphics shown are typical of a trial performed in controlled conditions. It is possible to observe the temperature increase during the physical activity on the treadmill and a slight decrease when the subject is at rest. It is also possible to observe the increase of relative humidity inside the footwear. Additionally, questionnaires including qualitative evaluation scales can be applied to a panel of users to evaluate their perception of temperature and humidity on foot and inside the shoe. To keep the thermal comfort of footwear, temperature should be in the range of 27 degrees Celsius to 33 degrees Celsius and the relative humidity in foot surface should be about 60%. The literature also indicates that the amount of heat generated or supplied to the feet must be compensated by heat loss, so the rates of heat generation and release must be similar to maintain the temperature and comfort range.
Thermal insulation. This section includes 4 subsections describing the test and recommended values of thermal insulation of materials and whole footwear. The insulation of footwear against cold and heat. Materials. Thermal insulation is a measure of material's resistance to transferring heat through its thickness. The thermal insulating power is expressed with thermal resistance that is directly proportional to the thickness and reverse proportional to the thermal conductivity of material. High thermal insulation means that heat travels very slowly through the material, causing the temperature to build up on the side of heat source. Thermal insulating materials are useful for footwear that is used in cold conditions, avoiding or minimizing the feet heat loss by shoe. In hot conditions, the use of insulating materials difficult the elimination of heat released by feet to the outside of shoe. The materials should be selected in accordance with the final use of footwear. The standards N 13521 and ISO 17705 describe a method for determining the thermal conductivity of uppers, lining and insocks irrespective of the material. In this test, a constant heat source is placed between 2 identical metal cylinders which are mounted with their axes vertical. A test material is placed in the top surface of the upper cylinder and a third identical metal cylinder is placed on the top of the test material so that all the cylinders in the test specimen are concentrically aligned. The heat source is switched on and the temperatures of the 3 blocks allowed to reach equilibrium. The thermal conductivity of the test specimen is then determined from the steady-state temperatures of the 3 blocks, the exposed surface area of the blocks and test materials and test specimen and the thickness of the test material.
Thermal insulation against cold. The footwear thermal insulation in cold conditions is a relevant aspect in some professional activities, where the workers are exposed to extreme temperatures, and in some countries, where the environmental temperature can drop to very low values, being uncomfortable and sometimes painful. In cold conditions, heat supplied by feet can fall to very low values, being important to use insulated footwear that keeps the heat generated by feet. The heat supplied in cold conditions can fall to very low values, being important to keep this heat inside the shoe. Standard methods are available to evaluate the insulation of footwear against cold, to be used in very cold environments. Basically, in this test, footwear is placed on a copper plate in a cold box at very low temperatures, for example -17°C during 30 minutes. A temperature sensor placed inside the footwear records the temperature fall. This test method is described in standards ISO 20344 and ISO 20877. The recommended values for footwear with thermal insulation against cold: the temperature decrease on the upper surface of the insole shall not be more than 10°C. Thermal insulation against heat. The footwear thermal insulation in heat conditions is a relevant aspect in some professional activities. For example, firefighters are exposed to extreme conditions during a fire, and military are exposed to very hot conditions during their missions as desert. In some countries, in summer the asphalt from streets can achieve very high temperatures. In these conditions it is necessary to use insulated footwear to avoid the transference of heat inside the footwear and minimize the conditions that promote the increase of temperature inside the footwear. The same standard methods describe a method to evaluate the insulation against heat. Basically, in this test the footwear is placed on a hot plate at very high temperatures, for example 150°C, during 30 minutes. A temperature sensor placed inside the footwear on the insole records the increase of temperature. The recommended values for footwear with thermal insulation against heat, tested in a hot plate at 150°C, the temperature increase on the upper surface of the insole after 30 minutes shall be not greater than 22°C.
Whole footwear. In the last years, technical scientific community has been investing in the development of new laboratory tests to study and evaluate the thermal insulation of footwear and develop more thermal comfort footwear. This figure shows a system of a thermal foot with 7 segments with independent control of temperature and with sweat points to simulate the transpiration. The thermal insulation can be determined with and without sedation. This type of test is useful to test and select the most suitable materials, depending on the final use, and optimize the footwear model. The test method is based on a thermal foot to determine thermal insulation of whole footwear as shown in the picture.
Softness and lightness. Leather softness. Softness is the distension of the leather produced when a cylindrical rod of defined mass is lowered at a specified rate onto a securely clamped area of leather. The standard ISO 17235 specifies a non-destructive method for determining the softness of leather. This method is applicable to all non-rigid leathers, for example, shoe upper leather, upholstery leather, leather goods leather and apparel leather. This test should be used more as quality control or to create comparative tests to select the most soft and light materials to be used in footwear manufacturing. There aren't available ISO recommended values for upper materials softness.
Materials lastability. Lastability is the ability of a material to be stretched simultaneously in all directions, distended, without being damaged. The standard ISO 17693 describes a test method to determine the lastability of uppers or complete upper assembly irrespective of the material in order to assess the suitability for the end use. Although this test is more related to the physical resistance of the materials, it can also be used during the assembly of a shoe to have an idea of the fitting ability of the upper material. Basically, this test method consists in testing a circular sample that is clamped round its edge and gradually distended by forcing a small metal ball attached to a plunger through the test sample. The first damage is recorded when, at a certain distension, either cracks appear in the surface of the material or a layer of the material sustains permanent physical damage. At a higher distension, the material usually bursts, and this distension can also be recorded. This table shows the requirements of lastability for leather and other materials used for uppers. For leather, it shall be greater than or equal to 7,0 mm, grain crack. For other materials, it shall be greater than or equal to 6,0 mm, first damage.
Lightness. Balance and length measurement device as shown in Figure 10. There is no ISO/TR guidelines available for upper materials and footwear lightness. In general, a light shoe is associated with higher levels of comfort. Nowadays, we see a growing interest in lighter materials by manufacturers, so that they can produce lighter products, responding to the demands of the market. These developments, which first appeared in sports footwear, are spreading to other types of footwear. The footwear lightness is one of the factors that influence the decision to buy. One method determines the mass and height of the shoe, and a rate is calculated to define the level of lightness. There aren't available ISO recommended values for upper materials or footwear lightness.
Longitudinal stiffness. Longitudinal stiffness is the moment required to twist the footwear. Flexibility is one of the footwear elements related to comfort that is appreciated by the wearers. Normally, the wearers prefer a flexible sole that promotes the most natural movement. This test allows one to measure the longitudinal stiffness of a complete footwear. The longitudinal stiffness test measures the force required to flex the footwear to an angle representing a 50 degrees flex of the foot or the maximum angle that can be achieved without exceeding a critical bending point. A product is considered extremely flexible if its stiffness is very low, less than 2 Nm. If the stiffness is between 2 and 3,9 Nm, the product is very flexible. Medium flexible if stiffness is between 4 and 8 Nm. It is considered stiff if it is between 8 and 10 Nm and very stiff if greater than 10 Nm.
Torsional stiffness. Torsional stiffness is the force required to flex the footwear to an angle representing a 50 degrees flex of the foot or the maximum angle that can be achieved, without exceeding a critical bending moment. The torsional movement of the foot is inhibited by the footwear when compared to being barefoot. In barefoot conditions, the foot adapts more easily to any perturbation by allowing the rear foot to twist, preventing some injuries in the ligaments, when compared to wearing shoes. So, to promote footwear comfort, it's necessary to find a compromise between the protection against impact forces and the loss of torsional movement. This test method measures the torsional stiffness of a complete footwear. In the torsional test, the shoe is twisted along its length to a fixed angle of twist. The torsional stiffness is recorded as the measured moment required to twist the test shoe. The recommended values for torsional stiffness are as follows: classed as flexible if stiffness is less than 1 Nm, medium flexible if stiffness is between 1 and 2,5 Nm, and stiff if stiffness is greater than 2,5 Nm.
Biomechanical comfort. Plantar pressure distribution is related to the pressure under the plantar surface to avoid areas of pressure that can provoke discomfort and, in extreme cases, injuries. Footwear construction should promote plantar pressure distribution, reduce plantar pressure and minimize the peaks of pressure.
Ground reaction, known as the impact force, occurs when the foot strikes the ground. The ground force reaction is a three-dimensional force vector that can be subdivided into its one-dimensional components, one vertical and two horizontal. The various forces are: vertical ground reaction force, anterior-posterior medial-lateral ground reaction force, and medial-lateral ground reaction force. The test method based on a mechanical foot is shown in Figure 15, Mechanical Foot System, for gait simulation. Plantar pressure. Ground reaction force. The test method based on a wear trial is shown in Figure 16. The selection of a panel of individuals, which can involve more than one group, depending on the aim of the study. Each individual wears the footwear for a period to allow the acclimatization of the foot to the footwear. The individuals are asked to walk in a natural and comfortable way in a defined path that integrates the force platform. The results are analyzed and interpreted, with regard to vertical ground reaction force, anterior-posterior medial-lateral ground reaction force, medial-lateral ground reaction force.
Shock absorption. Shock absorption is related with the absorption of impact forces, mainly on heel, during the walking. The shock absorption will reduce the potential harmful impact forces that occur during running, jumping and walking, among other activities. The recommended values for casual footwear are: maximum deceleration less than or equal to 200 meters per squared second. Return energy to confirm greater than or equal to 34%, maximum of 50%. The recommended values for town shoes with hard heels are: maximum deceleration less than or equal to 350 meters per squared second. Return energy to confirm greater than or equal to 32%, maximum 50%.
Cushioning. Cushioning is associated to the ability of shoe bottom to conform elastically to the shape of the foot and the plantar pressure distribution while walking or standing. Cushioning energy is the energy required to gradually compress a specimen of the material up to a standard pressure as measured. The specifications and requirements for occupational footwear is that the compression energy shall be greater than or equal to 20 joules. In the case of casual footwear, outsole, the compression energy shall be greater than or equal 15 joules.